Okay, so let's start the lecture. Okay, so we're going to first, as a warm-up, we have been considering the method of variation of parameter, or sometimes it's also called variation of constants. Okay, so variation of constants method. Okay, so we're going to kind of first review this method. Okay, so review this method by talking about an example. Okay, so let's look at this example. Okay, so this one says, okay, so can you find the general solution of this following equation? 4y double prime minus 4y prime plus y is equal to this. Okay, so it's 4y double prime. Okay, so 4y double prime plus minus 4y prime plus y. Okay, so minus 4 times y prime plus y is equal to, okay, so it is equal to 8 times e power t over 2 over t. Okay, so it's 8 times e power t over 2 over t, where t is positive. Okay, so that's kind of the equation. So by variation of constants, it means that, so we have two methods of solving non-homogeneous equations. One is the method of undetermined coefficients. The other one is variation of parameters, right? So you have to be able to choose among these two which one you would like to use. Okay, so what's the principle? The principle is that if the right-hand side is has quite standard shape, for example, cosine, cosine, right? So exponential or polynomial or a mini mixture of them, then you probably can use method of undetermined coefficients. Otherwise, usually variation of parameters is a more dominant method that can be applied no matter what your right-hand side looks like. Right? So here is an example. So here you can see that the right-hand side is something that's not very standard, right? So it's, it has a shape that's an exponential divided by a polynomial. We never talked about this shape. So we use variation of parameters, right? So we use variation of parameter method, right? So variational parameter method, first we should work with the complementary equation. So the complementary equation, so step one, right? So step one, you consider the complementary equation, right? So as we talked about last time, you consider the complementary equation 4yc double prime minus 4yc prime plus yc is equal to 0, and therefore the characteristics, right? So the characteristic equation has the shape 4r squared minus 4r plus y is equal to 0. So that's the same thing as 2r minus 1 square is equal to 0. So r1 is equal to r2 is equal to 1/2. It's just 1/2. Therefore, the general solution, right? So the general solution, so the general solution of the complementary equation. So that means we have to say that this is the complementary solution. Okay, so complementary solution. Okay, so complementary solution takes the form. Okay, so yc of t is c1 e to the power 1/2 of t plus c2 because the two rules are the same. So you're going to use the golden principle. You're going to multiply by t. So c2t times e to the power 1/2 of t. So one of them is going to serve as your y1 of t. The other one is going to serve as your y2 of t. So that's kind of, as I said, you have to pick up your y1, y2 according to your, I mean, you have to stick to your own choice of the y1, y2. You should never change your y1, y2 during the process of solution. If you choose, you choose, right? So let's say my choice is to say that y1 of t is e to the power 1/2 of t, y2 of t is equal to t times e to the power 1/2 of t. So that's the two fundamental solutions, right? So that's the two fundamental solutions. So let me say are the fundamental solutions. Right, so they are the fundamental solution. So the next step is to consider the non-homogeneous equation, right? So the non-homogeneous equation. The non-homogeneous equation has a non-zero right-hand side. So So that looks like 4 times y double prime minus 4 times y prime plus y is 8 times e to the power t over 2 divided by t. So that's kind of the this is the non-homogeneous equation. But in order to have the right-hand side, we should say that the standard form. Remember, right? So in order to work with the variational parameters, we've been emphasizing that you must turn the equation into a standard form. So in a standard form, it's y double prime minus y prime. So you have to divide by 4 on both sides of this equation. So 4/1/4 is 2 times e power t over 2 divided by t. This is exactly your g of t. This is your g of t, right? So you have to work with this form of g of t instead of the other 8 times e power t over 2. So you must work with this form of g of t. Now, once you have this form of g of t, you can start to apply variational parameters formula. So that means particular solution, right? So particular solution is going to take the form. What's variational parameter? Variational parameter means that you vary the complementary solution. The constants in the complementary solution are varied into functions. So that means capital Y of t, the particular solution is u1t of y1 of t plus u2t of y2 of t, right? So where y1 and y2 are already chosen, right? So that's u1 of t e to the power of t over 2 plus u2 of t t times e to the power of t over 2. So that's kind of going to be your particular solution. Where the u1, u2, remember, they follow certain formulas, right? So if you remember the formulas we talked about in last lecture, u1 is minus y2 multiplied by g divided by the Wronskian of y1, y2, right? So we've been talking about the rules, how to memorize this formula. The Wronskian must be on the denominator because something not equal to 0. Regarding the g, you must take the equation in standard form. If it's not in a standard form, you cannot use the g. And the y2 is minus y2 and plus y1. So u1 is minus y2 and u2 of t is equal to plus y1 multiplied by g divided by Wronskian of y1, y2. So that's going to be your u1, u2. So that means in order to justify everything, you have to calculate the Wronskian. So the Wronskian is not easy to calculate, right? So as long as you know the y1, y2, so the Wronskian of y1 and y2 is the Wronskian of the function e power t over 2, t times e power t over 2. So that's going to be the determinant, e power t over 2, t times e power t over 2. And then it's 1/2 e power t over 2, that's the derivative. And this derivative is e power t over 2 plus t over 2, right? So e power t over 2. So that's going to be e power t, t over 2, e power t minus t over 2, e power t. So that's just going to be e power t. So that's easy, a very easy Wronskian, right? So let me double check. Okay, so that's going to be very easy Wronskian that you calculate here. As long as you have the Wronskian, you can start to apply these formulas. So that means u1 of t. Remember, when you calculate u1t and u2t, as we explained last time, you do not really have to calculate the definite integral. You can just check the indefinite integral plus some constants. And you can pick the constants as convenient as you like. Okay, so you can pick any constant you like. So that's going to say, that being said, the u1 of t is a minus of y2. y2, remember, is t times e power t over 2. And what about the g? Well, the g is given by 2 e power t over 2 over t. So 2 e power t over 2 over t. And then divided by the Wronskian is e power t. So that means in the end, you're going to have e power t over 2 is cancelled. This one cancel. So that's minus 2t. Some people say we're going to plus c. But you don't really need to see this indefinite integral means that you can pick any other kind of antiderivative. Okay, so that we explained it last time. Okay, so if you are not clear with this, you can watch the video for the last lecture. Okay, so that u2 of t in the same rationale is the integral of plus y1 is e power t over 2. And the g is again 2 times e power t over 2 divided by t. the Wronskian is e power t. So this and this cancel is integral of 2 over t, so that you get logarithm of t. T is greater than 0, right? So that's, let's say t is greater than 0, you get logarithm of t. Okay, so that once you have the u1t and u2t, you can see that the particular solution can be written, right? So it can be written as 2t e power t over 2 plus 2 times, okay, so 2 times the, so minus 2t power t over 2, 2 times the logarithm of t multiplied by t e power t over 2. So that's going to be your solution. That's going to be your solution. Okay, so the last step is to combine everything, right? So let's say step 3. Step 3 is that you're going to combine everything. So the general solution, okay, so the general solution to the non-homogeneous equation, okay, so non-homogeneous equation, right? So the general solution to the non-homogeneous equation is going to take the form C1y1 of t, C2y2 of t, plus the particular solution to the non-homogeneous equation. That's the structure of the general solution of the non-homogeneous equation. So that's C1 e power t over 2 plus C2 t times e power t over 2 plus the capital Y of t is actually equal to a combination. So that's going to be minus 2t e power t over 2. This is the first part, plus 2t logarithm of t e power t over 2. So that's going to be your, according to this particular solution. So now you can see that in the end, it is written as C1 e power t over 2 plus C2 minus 2 multiplied by t times e power t over 2 plus 2 times logarithm of t multiplied by t times e power t over 2. So the C2 minus 2 is actually equal to another C2, maybe C2 tilde, if it is just another constant. So that means sometimes variation of parameters is going to give you solutions that are really in the complementary part, which can be absorbed into the complementary equation. So in the end, the solution is C1 e power t over 2 plus C2 t times e power t over 2 plus 2 times logarithm of t multiplied by t e power t over 2. That's the end of the problem. That's the end of the problem. Is that good for everybody? Okay, so that's kind of the whole procedure. Okay, so the whole procedure consists of 3 steps. First step is that you should work out the complementary equation. You obtain the 2 fundamental solutions. And then as long as you have the fundamental solutions, for the non-homogeneous equation, you have to justify what is your right-hand side, g of t, by considering the standard form of this equation. As long as you have the right-hand side, you have the particular solution as a linear, combination of y1 and y2, but with variated constants. This is the particular solution to the non-homogeneous problem. You have to variate the constants into functions, and these functions can be calculated using the Wronskian minus y2 plus y1 and the g in the standard form. So you just do a little bit calculation, and the good news is that the integral, you don't have to really evaluate the integral. You can just replace it by the antiderivative, then you're done, right? So, and that means you combine everything. When you combine everything, you should also aware that sometimes the part of the complement particular solution is going to be agreeing with part of the complementary solution, so that you get your answer. So that's kind of the whole procedure, how you work things out. Okay, so that's kind of the whole procedure, how you work things out. Okay, so that's kind of an example that I would like to show you regarding the variational parameter method. Okay, so here there are a lot of examples that I have been providing in my lecture notes just to help you review this part of the material. Okay, so they're synthetic, so that means it didn't really tell you use the method of variation parameter or method of undetermined coefficients. It's not clear which one you should use, but you should choose your own method. Okay, so that's kind of the exercises that you would like to practice. Okay, so that's all I want to say about the method of variation of parameters. Okay, so today we're going to talk about one more method. Okay, so today we're going to talk about one more method. It's called reduction of order. Okay, so Okay, so today we'll talk about one more method, which is called reduction of order, and it was usually tested. Okay, so it has been, it will be usually tested on your exam too. Okay, so very important method. Okay, so the reduction of order is a method that tends to give you an explanation. Okay, so it tends to give you an explanation. I mean, a mathematical foundation of the method of golden rules or golden principles, right? So remember, we have been using this method of golden principles just in case we want to find a set of fundamental solutions, right? So, and what is that golden principle? Golden principle says that if you're lacking solutions, you must multiply by t's, right? So that's the idea, right? So that's so let me write it somewhere. Okay, so we've been talking about this golden principle, right? So that's a golden principle. So maybe use this pen. Okay, so right, so okay, so the golden principle is such a principle. Okay, so right, so this principle is such a principle. It says that if you're lacking solutions, you should multiply by t's, right? So that's kind of it has been used in finding solutions. For example, when we have this, let's say, general solution to the homogeneous problem, we usually use c1t to the power of rt and then c2t times e to the power of rt, just in case that the two roots are the same, right? So if the two roots are the same, then you're lacking solutions. As long as you're lacking solutions, you should multiply by t. So that's the golden principle, right? So that's golden principle. That's why for these two solutions, roots are the same. Should you, okay, so should you multiply everything by t, right? So, and what's the rationale behind this method, right? So what's the rationale behind this method? So that's the method is about, okay, so it is about an equation. Let's say ay double prime plus by prime plus cy is equal to 0, right? So that you get ar squared plus br plus c is equal to 0. You get your two solutions. R1 is equal to R2 is equal to R. R1 is equal to R2 is equal to R. In that case, you want to try two solutions. One is e power RT, the other one is t times e power RT. Right, so that's kind of how you try it, right? How you try. Now, why is that the case? Okay, so is it just like an empirical principle, or is there a reason behind it? Okay, so the method we're going to introduce here is a so-called reduction of order method. Okay, so it's the method called reduction of order. Okay, so what is the reduction of order? Well, reduction of order is a much more general method for you to find a set of fundamental solutions. Okay, so for you to find a set of fundamental solutions. So what's the idea? Well, the idea is the following. Okay, so let's say if you have, let's say A is non-zero, right? So if you have such a second order constant coefficient equation and it has a double root, it means that both the roots are equal to minus b over 2a because, okay, so since the square root of b squared minus 4ac is going to be 0, discriminant is 0, this is the common solution, is minus b over 2a. You agree with me, right? So that's the common solution. As long as you have the common solution, I know, okay, so we know, okay, so we know that one of the solutions is y1 of t is e power rt. So that will be one of your solutions, right? So we know this is the solution, right? But what about the other solution? Well, the other solution, let's say, suppose you don't know the golden principle, then you're going to try you're going to try v of t multiplied by e power rt, where v of t is an unknown function. Okay, so that's what called reduction of order. Why it's called reduction of order? Because y2 is going to be a solution, so it's going to satisfy this equation. But this equation, since y2 is related to y1, by the e power rt. So basically, you want to try v of t. So basically, here I should say, okay, so I should say that I'm going to first try v of t multiplied by y1 of t. That's going to be v of t e power rt. Is that good, family? Okay, so that means you have the first solution. Suppose you know the first solution. Then you're going to try that the second solution is a multiple of first solution by an unknown function v of t. So they are related to each other just by a function multiple v of t. And therefore, in order to determine y2 of t, it suffices to determine v of t. So that's kind of the reduction process. Okay, so that's why we call it reduction, because we are reducing the search. We're reducing the search for y2 to the search for v. You just have to find a satisfactory v in order to satisfy this y2. Is a good, family? So that means you're going to say that a of y2 double prime plus b of y2 prime plus c of y2 is 0, because y2 must be a solution. But if y2 is equal to vy1, then you're going to see that y2 is vy1, and therefore y2 prime is v prime y1 plus v y1 prime, and y2 double prime is equal to v double prime y1 plus v prime y1 prime plus v prime y1 prime plus v y1 double prime, right? So, and you can see that this is nothing but v double prime y1 plus 2v prime y1 prime plus v y1 double prime, right? So that's going to be your solution. And as long as you have this, you can combine everything. So that's going to see that ay2 double prime plus by2 prime plus cy2 is going to be equal to y2 double prime. So a v double prime y1 plus 2v prime y1 prime plus v y1 double prime, right? So plus b of y2 is b of v prime y1 plus v y1 prime plus c of y2 cv of y1. So that's going to be your 0, right? So that's going to be 0. I mean, this is just calculating left-hand side. But the left-hand side, you can see that as long as you have the v, right? So as long as you have the v, this can actually be written as a, okay, so it's going to be a of y1 of v double prime. And then plus, instead of in terms of v prime, it is going to be written as y1 prime multiplied by 2a. Okay, so let me write in this way. Okay, so let me write in this way. Okay, so this one actually can be written as, so I have 2a v prime. There's a common v prime. So the v prime is common, and then it's a 2a y1 prime plus b, okay, so b of y1. So that's going to be v prime. And then going to be your v, okay, so v is going to be replaced by a y1 double prime plus b y1 prime plus c of y1. So that's going to be your situation instead of v in terms of v prime. So let me just write it more formally. Okay, so in the same form, v double prime multiplied by a y1. So that's going to be your it's going to be 0, right? So because according to this equation, it's going to be 0, right? So, however, you immediately observe that because y1 is a solution, okay? So y1 is a solution. y1 is a solution to the homogeneous equation, which means that if you put y1 here into the equation, this has to be 0 because it satisfies this equation. So you don't have to be bothered by the last term of your contribution. What about this one? Well, this one, you have to use this, you have to use the fact that y1 is equal to e power rt. So if y1 is equal to e power rt, so let's say y1 is equal to e power rt, then y1 prime is equal to r e power rt. And you can calculate that this 2a y1 prime plus b of y1 is equal to 2a r e power rt plus b of y1 is b e power rt. So that's going to be 2ar plus b multiplied by e power rt. Is a good, family? But what is the common root r? In the case that you have a double root, the r must be equal to minus b over 2a. So therefore, this is actually 2a multiplied by minus b over 2a plus b. multiplied by e power rt, which is exactly equal to 0. Is a good family. Okay, so that's a 0 again. So that's good news again that this will be 0. Is a good family, right? So this is going to be 0. So in the end, so finally, you're going to see that it just says v double prime multiplied by 2a e power rt is going to be 0 because y1 is equal to e power rt. We're searching for a factor. Remember, the philosophy is that we're going to say that the second solution differs from the first solution just by a function multiple. And you're going to determine that function. Is a good family. So y1 is already known as e power rt. So this a is non-zero. So remember, a is the leading coefficient. A is never equal to 0. So that means this one is not going to be 0 anymore. So that's the same thing as v double prime is 0. Is a good family. Okay, so some people is going to ask why you do this. Well, we do this because we don't know. Okay, so suppose you don't know. I mean, I want to derive the golden principle. Suppose you don't know the golden principle, then you're going to guess that the second solution only differs from the first solution by a function multiple v of t. And that's why we call it the reduction process. Why is it reduction? Because the original second solution y2 is going to satisfy a much more sophisticated ODE. That the differential equation has a lot of coefficients you want to from which you want to calculate the solution. But after you say that the second solution differs from the first solution only by a function multiple v of t, then the v of t only satisfies a much simpler equation. The equation for v of t is much more simple than the equation for y2. So that's why we call it reduction of order, right? So reduction of order. This order is not the order of the differential equation, but the order of complexity, right? So it reduces the order of complexity from a very complicated equation to a much more simpler equation. Is a good family? Okay, so that's why we would like to say that this is called reduction of order. Now, as long as you can apply this reduction of order, it means that it suggests it suggests that you can take v of t is equal to t, right? So let's say c1t plus c2 because we just want a function. Second derivative is 0. The solution is going to be c1t plus c2. So that means the first solution y1 of t is e power rt. The second solution, so the second solution y2t, so the second solution y2t is going to be equal to c1t plus c2 times e power rt. So that's kind of we just immediately obtained a much more general golden principle. Instead of just inserting t, you can insert a very general first order polynomial, c1t plus c2. They all work because they're all going to give you the second solution. However, the point here is that, we have to make sure that the round skin, right? So between y1 and y2 is going to be non-zero. The round skin is non-zero because you want to set the fundamental solutions, right? So remember, the general solution to this homogeneous problem should be a combination of the two fundamental solutions, but not the arbitrary two functions are fundamental solutions. They are round skin. They have to both satisfy the equation as well as the fact that their round skin has to be non-zero. So you have to really justify that the round skin is non-zero. Otherwise, you cannot say that you have obtained a set of fundamental solutions. Right, so that's the kind of problem. And what about the round skin? Well, the round skin is going to be e power rt c1t. So c1t plus c2, let's say multiplied by e power of rt. So that round skin is actually e power rt c1t plus c2 multiplied by e power rt. Right. So then you take a derivative is r times e power rt, and this derivative is going to be c1. So e power rt. Plus c1t plus c2 r times e power rt, right? So r times e power rt. So if you take that round skin, you can see that these multiples with these multiples are going to cancel. So the only thing left is c1 e power 2 times rt should not be equal to 0, which is the same thing as c1 should not be equal to 0. So the c1 should not be equal to 0. So that means when you find a second solution, you cannot just find a constant multiple of the first solution it has to be C1t plus C2, where the C1 is never equal to 0. Is that good, family? Okay, so if C1 is not equal to 0. So finally, it suggests, so a suggested fundamental solution. Okay, so by fundamental solution, now why I suggested fundamental solution? Because you only have to pick C1 and C2 such that Y1 and Y, you just want, remember, you only have to find 2 solutions, right? So you only have to find 2 solutions to the homogeneous problem, right? So such that, we always say that you have to be lucky twice, right? So let's recall the whole procedure of finding solution. The whole procedure of finding solution is a method of guessing, right? So you're going to just guess 2 solutions, and these 2 solutions, for second order constant coefficient equation, you want to guess 2 solutions, right? This is where we start from. And in order to make the guess, you're using the exponential function to do the guess. Is that good, family? Okay. So, but how do you guess? Well, you're going to guess 2 solutions such that their Wronski is non-zero. So a set of fundamental solutions, once you obtain them, then the general solution is just a combination of these 2. So that you only do a good guess. And what's your good guess? Well, this theory is going to tell you that the second solution can be guessed from a very general class of solutions, that the factor here is C1t plus C2. So no matter which one you take. So that means, for example, you take C1 is equal to 1. So you can take, okay, so let's say take C1 is equal to 1 and C2 is equal to 0. You just take C1 is 1, C2 is 0. Then you're going to get your solution. So the y1 of t is e power of rt. The y2 of t is t times e power of rt. That's going to be recover the golden principle, right? So recover the golden principle. It recovers the golden principle, right? So this is the way how you find a second solution from the first guess. So that kind of gives us a more thorough and solid method of guessing. As long as you have the second order homogeneous equation, you guess the one solution. Now you want to guess the other solution. How do you guess the other solution? Well, you're going to say that the second solution just differs from the first solution by an unknown factor function v. That's why we call it reduction of order, because you reduced the search for the second solution to the search of the v. And once you use this original equation, you find another equation for v. Usually the order of complexity of that equation is being reduced. That's why we call it reduction of order. As long as you find a v, you can determine the constants as you like, right? So, but just to make sure that the Wronski has to be non-zero. Otherwise, you're going to run into a problem. Because you want to find the 2 independent solutions, they have to be a set of fundamental solutions. So you cannot set the Wronski to be 0. The Wronski has to be non-zero. That will ensure you to be able to find appropriate C1, C2, usually 0s and 1s, like what I have here. And that's going to recover a set of fundamental solutions. As long as you have the fundamental solutions, the golden principle is recovered. Is that good, family? Okay. So the whole procedure that we introduced here is called the method of reduction of order. Okay, so reduction of order. So that means here it's a very general method, right? So it was we were applying it to second order constant coefficient equation. But in general, this is actually a method of guessing the solutions, right? So if you recall the whole principle of this chapter, we are actually moving from solving an equation to guessing an equation, right? So that's kind of the idea from the very beginning, is that in order to solve this equation, you just have to guess 2 solutions, right? So let's say if it is a homogeneous equation, then you just have to guess 2 solutions. You have to be lucky twice. And how do you be lucky twice? Well, you guess 1 solution, you guess another solution, and these 2 solutions, they have to form a set of fundamental solutions, okay? Fundamental solution. Namely, the Wronski has to be non-zero, okay? So the Wronski has to be non-zero. As long as you have this set of fundamental solutions, you're going to say that any solution is a linear combination of the 2. So that means, so we are going to pick, okay, so we're going to, so that's kind of the general method is going to tell you that if you have a homogeneous equation, okay, so if you have a constant coefficient homogeneous equation, you have one solution, candidate of the solution. You want to find the other solution, then you have to use this method called reduction of order. That's a good method. So that means you find one solution y1 of t. Now you're going to suppose the other solution differs from the first solution by a function multiple v of t. Now instead of looking for y2 of t, you're only looking for v of t. So that's the idea. Okay, you plug in y2 to the equation, you get an equation for v of t. Usually, the equation for v of t is much simpler than the equation of y2. So that's why we call reduction of order, because you reduce the complicated equation for y2 to a much simpler equation only for v. Okay, so as long as you have this, you solve for vt in general form that contains constants. But you have to check that the Wronski is non-zero to determine the good constant C1, C2. Remember, the whole theory is about guessing. You guess the one solution, you want to guess the other one. So that means you don't have to really work with a very general C1, C2. You can just work with a candidate. So usually the C1, C2 are picked as zeros or ones. You're going to pick up the solution. So that's going to be an idea. Once you get a fundamental set of solution, the general solution is just a linear combination of these two fundamental set of solutions. Is a good family. Let me remind you by the end of this procedure that the whole procedure is used to look for two fundamental solutions for a homogeneous equation. Remember, if you have a homogeneous second order equation, you only have to do two guesses, right? So you have to be lucky twice in the sense that you want to find two fundamental solutions. But if you are working, let's say you are working with a non-homogeneous equation, then you have to be lucky 3 times, remember? Because you want to find a complementary solution, and in order to have the complementary solution, you have to be lucky twice. But that's not enough, because you have to also find one particular solution to the non-homogeneous problem, so you still have to be lucky one more time, right? So that's kind of the thing. So we have to be clear that in order to apply this reduction of order method, we just have to be lucky twice. Is a good family? Okay, so you just want to find the second solution. So this method is going to be applied to homogeneous equations, right? So right-hand side must be equal to 0. You only have to be lucky twice. That's a method for you to find fundamental solutions for the homogeneous equations. Is a good family? Okay, so let me show you an example. Okay, so let me show you a very nice example. The example says that given that yt, so this is kind of very general. As I said, the reason why we want to learn the method of reduction of order is that it has a much more general power. Okay, so for example, here it says you're going to see this equation, t squared y double prime. Okay, so t squared y double prime plus, okay, so minus t plus 2 of y prime. Okay, so let's say minus, okay, so minus t plus 2 of y prime minus t plus 2 of y prime. And then it's plus t plus 2 of y. Okay, so is 0. So that's kind of a constant, it's not a constant coefficient equation anymore. So you cannot just use the simple golden principle multiplying by t, but you have to look for your own golden principle. Is a good family, right? So the golden principle that we have talked before was just a method of finding the solutions to the constant coefficient equations. Is a good family. But in general, if the problem looks like this, then it's going to say that the first solution is equal to t. So you never see even e power of something, because this is not a constant coefficient equation. The previous theory never applies, and you have to look for something new. Is a good family. That's why we want to use reduction of order. And I would like to also remind you that this is the typical shape of the problem when you when they want to test you reduction of order on an exam. This is the typical shape of the problem. The problem is going to say, given that first solution is something of this homogeneous equation, can you find the second linearly independent solution? So how are you going to do that? Well, you're going to set y2 is a v of t multiplied by t. Or sometimes we can just suppress the dependence on t or say vt, where v, but you must know that v is not a parameter, v is a function. Is a good family? Okay, so there's a reduction of order. You reduce the second solution, the search of the second solution, to the search of an appropriate v, a search of an appropriate v. So as long as you have this, you can see that y2 prime is going to be v prime plus v prime plus v, let's say v prime t plus v, and y2 double prime is a v double prime of t plus v prime, right? Plus v prime plus v prime. So that's v prime plus v prime. So v double prime of t plus 2 times v prime. So that's going to be your y2. And therefore, because y2 satisfies this equation, so that means you're going to have, okay, so you're going to have t squared of y2, so 0 is equal to t squared y2 prime minus double prime minus t plus 2 of y2 prime plus t plus 2 of y2. You're going to insert all these values, so the t squared of v double prime of t plus 2v prime minus t multiplied by t plus 2 of y2 prime is v prime t plus v plus t plus 2 of y2 is equal to vt. So that's going to be your 0, right? So, but what will be your solution? Well, again, you're going to collect according to the order of the derivative of v. So that means v double prime multiplied by t cubed. That's the first solution, first part. And then plus v prime, you're going to have 2 times t squared, right? So 2 times t squared. And then here you have another v prime, right? So v prime is going to be, so it's minus t squared t plus 2. So that's going to be your v prime, right? So t squared t plus 2. And then what about the v? Well, it's going to be plus v. And then the factor is minus t plus 2, let's say minus t multiplied by t plus 2. This is the coefficient for v. And then plus t multiplied by t plus 2. That's another coefficient for v. So you can immediately see that these two are going to cancel. They're going to give you 0. And for this one, the 2t squared is going to cancel with the 2t squared. So the whole thing is going to give you t cubed. The v double prime minus v prime is going to be equal to 0. Is a good family, right? So this is a calculation that you can see that 2t squared of v prime, and this 2t squared is cancelled with t squared multiplied by 2. So in the end, you just left with minus t cubed and plus t cubed. So that's going to be your equation. So this actually means that the solution is v double prime minus v prime is 0, because the t cubed is never going to be 0 if, let's say, t is positive. Is a good family? Okay, so that's v double prime. So you can see that the original equation, right? So the original equation, including the y's, is kind of impossible to solve, because we have never been talking about any explicit method to solve this equation. Is a good family, right? So, but rather you have to guess by the first solution he told you, and the second solution by the reduction of order. We're talking about this reduction of order method. The second solution is by the reduction of order. There's going to be an order v, and once you have that v, the v must satisfy this equation. Okay, so the v must satisfy. This was a solvable equation. It's much simpler than the original one. So that's why it reduces the order of complexity. That's why we call it reduction of order, right? So how do you solve this equation? V double prime minus v prime is equal to 0. You can use the second order theory, but let me say, okay, so let me say a much simpler method. I will let v prime is w, then the w prime is equal to w, because the v prime is w, v double prime is going to be w prime. So for what kind of functions is derivative itself? It just tells you that w is equal to e power of t, right? So let's say e power of t multiplied by constant, c1 e power t, c e power t. Is a good family, right? So w is just an exponential function. It's only exponential functions, the derivative come back to itself. But if w is that function, v prime is c, let's say c1, okay, c1 e power t, is going to tell you that v is c1 e power t plus c2. So that's going to be your v. Is that good, family? Okay, so that once you have the v, you can come back to this solution. It means that y1 of t is equal to t, and y2 of t is c1 e power t plus c2. So that's going to be your fundamental solution. But this is not enough. As we said, you have to check the Wronskian. So remember, this is a very important step that you should never miss. Okay, so it doesn't mean that once you find C1, C2, that's combination, you're done. You're not done because you want to calculate the round skin. So that's T, C1 e power T plus C2, your derivative is 1, C1 e power T. So that's going to be your derivative, right? So that's going to give you, okay, so it's going to, so just a moment, okay, so let me just double check that I'm still there, okay, so let me just double check that I'm still there, okay, so that's going to be T, okay, so let's say V prime, okay, so it's, okay, so that's going to be a derivative, okay, so this is going to, the round skin is, sorry, so this one should be multiplied by T, I've got. Okay, so this should be multiplied by T because that's the V multiplied by T, right? So the second solution is the first solution multiplied by V, right? So that's V multiplied by T. So you take a derivative, that's going to be C1 e power T multiplied by T plus C1 e power T plus C2. When T is taking derivative is 1. So that's going to give you that the round skin is actually going to be C1 T squared e power T, because C1 e power T, T, there T squared. And then this one multiplied by this one cancels with this product. So that's going to be non-zero, which means that C1 has to be non-zero. C1 has to be non-zero. So it doesn't quite matter which you pick for C2. So that means in the end, we're going to say that we pick C1 is equal to 1, let's say C2 is 0, then you're going to get a set of fundamental solution. Y1t is T, Y2t is T e power T. Is a good family, right? So Y1t is T, Y2t is T times e power T, because I pick C1 equal. So in this case, this is not really the golden principle that you see before, because it's the golden principle that inserts, instead of inserting T, it inserts in e power T. So that's kind of an alternative golden principle. I mean, it inserts, instead of T, it inserts e power T. Is a good family, right? So if you come back to this equation, you can see why it's the case. Because the equation is never going to be constant coefficient equation. It's a very general homogeneous second order equation. It just tells you that if the one of these fundamental solutions is T, the second fundamental solution is T times e power T. So that means the general solution, okay, so the general solution is y of T is equal to C1 of T plus C2 T times e power T. So that's kind of a much more general way to find the solutions. Is a good family? Okay, so this is the power of this method of reduction of orders, because it can help you to solve a very general form of this second order equations with constant with zero right hand side, homogeneous. Is a good family? Okay, so this is a very important method called reduction of order, and I'm sure it will be tested on your upcoming exams. Okay, so I'm sure it will be tested on your upcoming exams, exam 2. Okay, so let me briefly review this method. It's like, first of all, we have to make sure that this is a method that applies to homogeneous equations. It might not be a constant coefficient, but it will be a second order linear homogeneous equation. And once you have that equation, you know that you only have to find 2 solutions. You only have to be lucky twice in finding 2 solutions that form a set of fundamental solutions. As long as you have done that, the general solution is just a linear combination of these 2. Now, the reduction of order is such a method that if you know the first solution, then you're going to just say the second solution differs from the first solution by a factor function, v of t. And then you reduce everything to finding the v of t. And in order to find a v of t, you have to use the original equation that y2 satisfies this equation, so that vt is going to satisfy a much more reduced equation. That's why we call it reduction of order. Okay, so from that reduced equation, you solve for v, but the v usually involves some constants. In order to eliminate the constants, you have to know that the round skin is non-zero. If the round skin is non-zero, then you can pick either 1 or zeros for C1, C2. You get the V, you get the second solution, and you are done. Is a good family? Okay, so that's kind of a method that I would like you to practice a lot of times before you go to the next exam. So here is another example, and here is another example. I give you quite a lot of examples. Some of them you have to find them on the student resources page because I didn't copy here, but I give you the reference exam and the year of the semester so that you can find it on the student resources page. Remember, the course has a student resources page which you can make use of. Is that good for everybody? Okay, so then you can find what you need. Okay, so this is a very important method. That's a method called reduction of orders. Reduction of orders. Okay, so that's what I want to say for today's lecture. Let's come back in the next lecture, and we're going to continue with the class. Okay, see you in the next lecture.